Okay, so here's example number 2. According to a recent government report, only 16% of occupants in trucks wear seatbelts. That's pretty low, right? Suppose you randomly sample 3 occupants of trucks. What is the random variable, and what would you tend to doubt the 16% estimate if none of the 3 were wearing seatbelts? Okay, let's see. Well, probably in order to create a probability distribution, we'd want to decide on what the random variable should be. And we eventually want to know, okay, what if none of the 3 are wearing seatbelts? So maybe we want to know how many seat-belted passengers, right? So seat-belt passengers, right? So we could have 0 seat-belted passengers. That's our none of the 3. We could have 1, 2, or 3. And we'd also want to know what's the probability of these seat-belted passengers, right? All right. So now we want to figure these out. Now, if this was like heads or tails, all of these combinations would have equal probability. But these don't all have equal probability because only 16% of occupants in trucks apparently wear seatbelts. So although it's useful to have the sample space, and I'll put the sample space here, this is not going to be enough. So first, let's just look at the sample space. So here's seat 1, 2, and 3. And I'll put an S for seatbelt and an N for no seatbelt, right? So here, half of these are seatbelted, half are not. All right, so here's our sample space. And we see that the 3 people all wearing seatbelts, right here, that's 1 out of 8 of the sample space. And this is also 1 out of 8 of this entire sample space. But the story is not that simple, because that would only be if wearing a seatbelt and not wearing a seatbelt were equally likely. But that's not actually the case. But these are independent events, right? So we could use the multiplication rule and think about, okay, let's say we have these 3 spaces. What is the probability that this guy here is not wearing a seatbelt? Well, that's going to be 84%. 16% wearing the seatbelt. The other side of that lopsided coin is 0.884. And so that is the probability for each of these seats, and we could think of them as independent events. Now, on the flip side, for number 3, where all 3 people are nice, seatbelt wearing, good, law-abiding citizens, right, in this pickup truck, that's going to be 16 to the 3rd power, right? But these are a little more complicated. Here, let's think about this. What's the probability that one person is wearing a seatbelt? So this guy, one of the seats, right? But these guys aren't, or these people. It doesn't have to be guy. Right? But this is much more likely also in the sample space. So there are 3 of these. So here's 1, here's another one, here's another one. And so using the addition rule, we would add this 3 times. But we could also just multiply it by 3. That makes it easier. All right. So what about if 2 people are wearing seatbelts and 1 person isn't? Well, that would be 0.16 for the 2 people wearing seatbelts. That's the proportion of the time that's the probability that they'll be wearing a seatbelt, times 0.84, the probability that this person won't be wearing a seatbelt. And here we see that there are also 3 cases. And so we could use the addition rule and add this 3 times, but we could just multiply by 3. All right. So once we do that, then we could see the actual probabilities. Here, we don't need to multiply by anything because there's only one, so it's really like multiplying by 1, right? And we can multiply this by 1 too if we wanted to. So I'm just going to calculate this in my Excel file. So I could put in 0.84 to the power 3. So that's 0.84 times 0.84 times 0.84. And that's 59.27%, or 0.5927. Oh, I don't know why I said 0.86. That's strange. All right. So this should be 0.5927, right? We could do the other ones just to finish it up. 2 times 3 times, sorry. 3 times 0.16 times 0.84 times 0.84. All right. And the next one is 3 times 0.16 times 0.16 times 0.884. And the last one is 0.16 to the third power. Okay. So we see that it's very likely for all three of them not to be wearing a seatbelt. It's less likely than this, but still pretty likely. About 34% of the time that your sample will have one person wearing a seatbelt. It's even less likely that 2 people would be wearing a seatbelt. That's only like 6%. And it's less than 1% chance that all 3 people will be wearing a seatbelt, right? So here, I'll just write these in. 0.337, 645, 0.0041, right? And so, would you tend to doubt the 16% estimate if none of the 3 were wearing seatbelts? Well, we know that if we took a sample, 59% of the time, that sample will have 0 people wearing seatbelts, right? So it's pretty likely that that sample is consistent with this estimate of 16% of occupants in trucks don't wear seatbelts. So we wouldn't necessarily doubt that 16% estimate. It might still be wrong, but we have no reason to doubt it. All right, here's example 3. So Apple is trying to get you to buy the AppleCare warranty for $250 for your laptop. If you buy this AppleCare thing, you'll get unlimited number of free repairs. But if you don't, you must pay $150 per repair. You find this information below on the web. What is the random variable here? And according to this data, is it worth getting the warranty? All right. So here you sort of want to predict, okay, how likely is it going to be that I'm going to need a whole bunch of repairs, right? Because if I need only 1 repair or 0 repairs, right, then I probably shouldn't buy this laptop warranty thing. But if I'm going to need to get it repaired pretty frequently, then I probably want to buy the warranty. So here, we can see the probability of the repairs listed here, and here are the repairs. And so this probability distribution has the random variable of repairs, right? And according to this data, is it worth getting this warranty? Well, one thing we want to do is probably look and see what the expected value is. So on average, over many people buying these laptops, what is the likely value of repairs? Like, so how many repairs am I going to need on average, right? Well, I have put this data on this table here in example 3. So it's the same table. And so it might be nice to find the expected value. So expected value of x. And in this case, x is repairs. And in order to find that, we want to find the contribution of each value of this random variable, right? So it's this times how likely it is. So 0 contributes more than 4 because it's much more frequent that people have only 0, they need 0 repairs, right? And then we add these all up. And remember, our expected values is repairs, right? So we, on average, will expect about 1.1 repairs, right? So no one person will need 1.1 repairs. You can only have one repair or two, right? But on average, it will average out to 1.1, right? Now, remember, this is in repairs. We don't know how much it is in dollar amounts. But if we wanted to know in dollar amount, right, we know that each repair, like if we didn't buy the warranty, would cost $150, right? So that would just be this times 150. So on average, we would expect to spend $165. Now, is that going to make AppleCare worth it? Well, I would probably say, according to this data, it's highly likely that you'll need, on average, 1 repair-ish, right? So it's probably not worth getting AppleCare. But if you want to be on the safe side, you could always buy it too.